So, in the last class, we discussed vectors and tensors, and we did some vector operations in terms of the components. In this lecture, we will discuss tensor operations in terms of its components. How to write tensor in terms of its components. Okay. Okay. Last class we discussed how to write a vector. So suppose this is a v vector of three components, let's say v1, v2, v3 in the x, y, z directions. So we can simply write this as chronicle delta I and vi, where let's say this starts from 1 to 3. This means what? Delta 1 v1 plus delta 2 v2 plus delta 3 v3, right? So delta 1 stands for the direction, let's say I cap, and v1 the component, scalar 1, delta 2 j cap, then we have v2 or vy or so on, right? But how to write the tensor? Let's say this is a tensor. I told you curly braces mean tensor, or you can write like this, double dash. So how to write this in short notation? You can also write in metric notation. So in matrix notation, this is like this: tau 1 1. Okay. Then you have two directions: 1 1, tau 1 2, right? Delta 1 delta 2, tau 1 3, row 1. 1 means first index means in the row 1 or the component of tau in x direction, right? And tau 3 delta 1 delta 2. So we'll discuss this. So before so on. So you have learned this is your cross product, this is your vector product, this is your dot product or scalar product, this is your vector product or cross product. Then there is third product called dyadic product, right? So what is dyadic product? Dyadic product means, suppose generally I cross j means what? I cross j is k cap, right? What is I dot j cap? This is 0, right? Then dyadic product means if there is no operator in between this, let's say there is no operator in between this I cap, so it is I. We write it like this, or we simply like this, delta I, right? This means this is a tensor, okay? This is dyadic product, okay? So we also know that we have double products, right? Double dot products. So single dot and again single dot, so double dot. So what will the output? So you can simplify it. So just separate these two first. No, this jk will come first, then I and L will come first, right? So jk, delta jk and delta IL. So the thing is, this is scalar, right? So what is the order of tensor? This 2. And if you have double dot product, that means it is 4. But if you have single product, this is 2. So 0. How? So if you do here, so we have 4 vectors: 1 2 1 2 3 4, right? So total summation is plus 4, and we have 2 dot products, double dot products. So 2 into minus 2, that is minus 4, so 0. The output will be your scalar. So this is scalar. Similarly, here we have 3 vectors, 1 plus 3, right? Order will be 3 and minus 2, 3 minus, so this should be a vector. So you are getting here vector, right? And so on. You can calculate the order. So what is tensor? Basically, to define a tensor, you need 2 directions. Okay? So suppose It's like if you study Newton's law, then you have tau yx, right? This is a tensor component actually. Okay, so this means, let's say you have a surface. So what is the y surface? Definitely this one, right? If you do like this, if you this is your coordinate system x, y, and z. So in up direction, this is your x. So this surface normal is the direction of this surface is your ay, right? Cap. So this is the area normal. Okay? And what is x? So suppose on this surface some force is acting in x direction, right? There is some kind of shear force, right? So this is shear force. So that's why we need two directions in tensor, right? So delta 1 means this both are pointing in the same direction. How? Delta 1 means it is delta x, right? So what is the surface here? If you follow this coordinate system, so we have x direction here, right? What is the direction of this area? X. If force is acting in the same direction, so the x. So delta 1. This is a tensor. Basically, this is normal stress represented in Fx or sigma 1. Okay. If it is shear stress, we'll denote it by tau. Here, if you see this one, let's say this one, daughter. So first one is what? In one direction. So it's basically acting in x direction, right? So in our diagram, x means this direction, right? And another force is acting in second direction. In second means y direction. In this diagram, this is upward is y. So this direction, y is acting in this direction. So this is shear stress, definitely, right? So you write it as first, what is the direction of the area in x direction? What is the force direction? We are applying force in y direction, so tau x y, right? And so on. So you can expand tensor in terms of its components. So basically this one, tau 1 plus tau 1 2 plus tau 1 3. So delta 1 it is sx. Okay. So on. You can write simply like this, right? So also you can write tau in terms in vector form, right? So this one is your tau x, and this one is your tau y, or you can say vector in second direction, and this is your tau z or tau 3. This is vector. Okay, so you can write it like this. Tau is a tensor. You can write in terms of vectors. That is your so if you see the first one, this is delta 1. So this is nothing but your since you have to respect the order of this thing, so you have delta 1. Okay, then you can write the components tau 1 delta 1 plus tau 1 2 delta 2 plus tau 1 3 delta 3, right? So you can write you can say this is your tau 1 delta 1. So tau 1 is vector. Okay. Similarly, you can write tau 2 vector as this one. Okay. You can also write the tensor in the matrix notation. Okay. So tau 1, oh sorry, 1 tau 1 2 tau 1 3. Here it is a third row, so tau 3 and first component, third row, second component, I will go continue. So this is your first vector, this is your second, this is your third, right? Okay, so you already know when tensor is called symmetric, when the opposite, this opposite are equal, right? Then it is called apart from the principal diagonal component, the opposite, if they are equal, then it is called symmetric. If they are equal but in negative sign, it is called antisymmetric. You already know this from matrix algebra. Okay, so what about the transpose over tensor? So just flip this up. It was ij previous, so just ji. Now, if you multiply two vectors without any operator in between them, so this is the additive product, you will get a tensor, because what is the order of vector? 1 plus 1, so that is 2, the order is 2, so you will get tensor if you have uh, the additive product of two vectors, right? This will be evident in your Navier-Stokes equation when you have this term rho vv. This is convective term, when that is basically a tensor only. Okay. How about if you want to know the magnitude of the tensor? Just simply do this. Half of magnitude of the tensor tau, half of double dot product of two tensors. Basically, you have to take transpose, right? So you will get the magnitude of this tensor. Addition of tensors. It is straightforward. If you want to add two tensors, so it is straightforward. So add two matrices, addition of two matrices. If you add addition to, you simply add the component wise, right? So that is same for the tensors. What about multiplication of a tensor by a scalar? It is also same like multiplication of a matrix by a number, right? So you have to multiply each component by the 3. Yeah, you can see here. What about dot scalar product or double dot product? See, if you want to make two, product of two tensors scalar, then you have to use double dot product. That is, you have to use double dot product. Right? These two are tensors. So what is the order of tensor? 2, 2, 2 plus 2. And what is the single dot product means? Minus 2. You have two double dot product, so minus 4. So it is 0. So you are getting scalar. So if you use double dot product of tensor, then you will get scalar. Okay. Similarly, if you see here, what will be the output? The output will be scalar only, because tau is a tensor and you have two vectors, the additive product, that is also tensor. So tensor, double dot product tensor will give you scalar. Similarly here, we have two vectors, the additive product of two vectors here. So this is tensor, and I have two dot products, so it will give you a scalar. Sorry. And suppose you want to do a dot product, single dot product, okay, not scalar product, it is tensor product or single dot product here. So what you will get? So you have order 2 minus dot product minus 2 and again plus 2, so you will get again tensor, right? You will get order is 2. So if you do a single product of two tensor, you will get tensor itself. You will get a tensor as a product. So it is called tensor product or single dot product. What about vector product? Vector product or dot product? Why we are saying dot product of a tensor? Because this is, we are using one single dot. Because the product is vector. See, we have a tensor and we have a vector here. So what is the order of tensor? 2 minus 2 for single dot product and plus 1. So this cancels out. The order is 1. So you are getting vector. If you do a single dot product of a tensor and a vector, you will get a vector. What about if you do a cross product of a tensor with a vector? So we are doing cross product of a tensor with vector. So what is the order of the tensor? 2. And cross means minus 1. What is a vector? Order 1. So you are basically getting a order of 2. That means you are getting a tensor, right? That's why it's called tensor product. We have certain operations here. Okay, you can derive this, or you can remember these formulas. Okay, we can go through these exercises. So to clear the concept, I will show you how to evaluate this one. Then you will understand how to do this dot product. Okay. So we have a kind of matrix here, right? And we have a vector. We want to do a dot product of a vector, right? So I will write vector in this column form. So we have v1. What is v1 value? That is vx. That is 5. So let me erase this. So we have 5, first component 5, then second component 3, then this is minus 2. So how to calculate this, right? It's simple. You just take this as a matrix multiplication. Okay. So first one is what? 3. Then 3 this multiply this multiply this, right? And add them all. Okay. So first try to do what will be the output. So the order of tensor is 2. Then you have a single dot product is minus 2. Then you have a vector 1. So it should be a vector, right? So we should get a vector. So we'll get a output as a single column. Okay. So 3 into 5, 15, 15, right? Plus 3 into 2, 6, plus minus 2 into minus 1, that is 2. So what is the output? 15 plus 6, 21. 21 plus 2, 23. And similarly, you can get the second by doing the same multiplication and summation, right? What about the directions? So tau xx, right? So this is what is this thing? First component, it is delta x, right? This is a vector, first component. This is delta y. This is delta z, right? So you're doing dot product, right? So what is the direct product of this tau xx? This means 3 delta x, and you're doing dot product with what? The first component of this. So that is your 5 delta x. So these are scalar. You can separate it. So this becomes 15. Remember to keep the same order. We have delta x, then delta x here, and dot delta x. What is the dot product of xx? That is 1, right? So 1 cancels out. So this becomes delta x. So, right? Similarly, this will be delta x, right? It is also delta x. The direction of 6 will be delta x. How? So you just do this 2. So we have 2 delta x. We are doing this one, delta x, then delta y. We are doing dot product with what? This second component of the vector, that is 3. 3, we have delta y, right? So dot dy because 1, 2, 3, 6, 6, and what is left? Delta x. So all these three have the same direction, that is delta x. That means we are getting a vector in this form. Okay. So rest you can do it. Just try to practice so that you can understand. Okay. So in next class we will discuss the vector tensor and differential operators. Okay. Differential in the sense dou by dou x1, dou by dou x2. It is nothing but dou by dou x, dou by dou y, like that. Okay. We are doing just x1, x2 because we have to learn these operators in 3 coordinate systems: rectangular, cylindrical, and spherical. That's why it is a general notation x1, x2, x3. Okay. So in next class we will do how to operate these operators on vectors and tensors. Thank you.